Hi, we're back again, and it's back for electronic stuff. So we are going to finish up my little detour about resistance, with the basics of resistance, and in particular resistors and LEDs. So in the previous video, which went on for a long time, I talked about voltage dividers essentially. So when you have two resistors in a row, what happens and how does the voltage get distributed across each thing. So the voltage up here is the positive voltage, and it has to, this is the ground voltage or the reference voltage down here. So there's a difference in voltage here, a potential difference. And so that voltage has to kind of be used up to get back down to here. And the way this happens, so in this example, if you have a 100 ohm and a 200 ohm resistor, you're going to end up with 2 volts across the 100 ohms and 4 volts across there. And the ratios are the same. So this is 1/3 of the total resistance. So the total resistance for resistors in series is, you add them up, so 100 plus 200 is 300. So this 100 ohms is 1/3 of 100. And 200 ohms is 2/3 of 100, and the voltage across, so in this case here I'm pretending there's 6 volts, so I didn't mention that bit. The voltage across the whole thing, so 6 volts at the top goes down to 0 volts, or ground. Because this is 1/3 of the resistance, we've got to use up 1/3 of the voltage, so we get 2 volts across there. And then we've got 2/3 of the resistance, so 2/3 of the voltage across there. That's just the way of writing the maths. So 200 over 100 plus 200, so total resistance, and that times 6, and that's what 4 is, and the same for the top part. So that was, hopefully in the last video, that was kind of came through. If not, it will come up again as we go along. But just wanting to finish it off with talking about, there we go, I'll put that away for a second. Talking about LEDs. So LEDs aren't resistors, but so far, and in everything you do, you'll probably put a resistor in series with your LED. So, oops, that's the wrong one. Uh-oh. Where did I put? Oh. Sorry, we're going to have to use this one. I accidentally drew all over the top. So this is my LED. I knew there was a purpose for the piece of paper. Sorry, I got to stop using these felt tip pens. They're terrible. They go all the way through the pages. I had a much better. Oh, seriously, it's right here. I was going to use this one. Anyway, that doesn't matter. The point is that, so we have in this case a resistor and an LED. Now it doesn't matter, by the way, so if you swap these two around. So if you had the resistor first and the if you had the LED at the top and then the resistor going through afterwards, that's fine. It doesn't really matter in that terms, as you'll see as we go along, because they're in series. But the question is, does it work the same way as the voltage divider? So does the LED act? See, it came through the page. Does the LED in fact act like a resistor and have a resistance, and therefore that's how we know what's going through there? Well, not really, but I mean it kind of does. Like everything has a resistance, and that will make some things change as we go along, as you'll see. But that's not the real trick with them. So with diodes, the trick here is that they have a certain amount of voltage that they basically need in order to allow current to go through. So this is their forward voltage. So for a standard, do I have a standard diode sitting around somewhere? You'd think I would. Hold on, I'm going to find one. There's bound to be one sitting. Just when you thought I was prepared enough. What's in this box? There's bound to be something in here. Bound to be. No, there's everything else but a diode. What's that thing? No, what's those strange bits in here? Kind of feel that would be important to talk about diodes. We can leave it later. The point is, diodes have the characteristic I'm going to get a cough again, that they only allow current through in one direction. But in order for that current to go through in that direction, you need a certain amount of voltage, and this is called the forward. Oh, look at this, there's a little bag here, and this has got some diodes in it. So these are diodes. So this diode here is probably a Zener diode. Yes, it is. So this is a Zener diode, but we'll just imagine for a moment. We're going to go through Zener diodes later on. So this thing here, in order for current to flow through, a certain voltage has to be used up, and that's a kind of fixed voltage. So in the case of a normal little diode like this, it's about, I think, 0.6 volts. Right? So if the current going through here, it's going to use up 0.6 volts. So I mean, we might just show that. So I'm going to stick it into the circuit here. This is going to be very hard. Oh, these are very, very stiff things. Maybe we won't. Okay, we won't. Just trust me on that. When we measured it, it would be 0.6 volts across there. And we can kind of pretend for now that it doesn't actually it doesn't have any resistance. It just uses up 0.6 volts when you go across, no matter what the current is. And resistors LEDs are kind of the same. It doesn't matter what current is going through, the voltage drop is pretty much going to be the same. That's not strictly true because, as I just said, it does have some internal resistance, but we can imagine it's quite low for our purposes, but it still has this needed voltage drop. So if we measure, so I've got this here, I'll turn this on, hopefully you can see everything, and then I will measure the voltage across. Oh my goodness. Alright, and oh, come on, stay on, light. I don't know how to get the light to stay on. If I measure it across here, you'll see that it comes out at 1.95. So I'm going to try a little trick. I'm going to take the voltage down. So this thing here, you can change it from 5 volts to 3.3 volts. So if I put it on 3.3 volts, it still turns on. Sorry, it's a bit dimmer. But then we're going to measure the voltage across here, and it's 1.87. So it's 1.87. So that's still roughly the same voltage. But if you look at the resistor, so here with the resistor at 3.3 volts, we get 1.40 volts across, which makes sense because 1.4 plus 1.87 is pretty much 3.3 volts. So the total voltage is 3.3 volts, as you expect. So if I put it back up here, you'll see I've only got 25 minutes on this one today because I'm running out of space on the camera again. It's 1.95, so a little bit higher, but the voltage across the resistor is much higher. So now it's 3 when it was like 1.4 before, so it's over twice as high. So all the voltage is pretty much going over the resistor, and the voltage across the LED is pretty much fixed. So if we put in a blue one, we can try this one for a second. So I was going to do some tricks here. Don't want to go into too long. Well, there's kind of interesting things going on here. So if we do this one and we turn the light back on, probably didn't see, maybe you didn't see the last stuff because it's all dark. Okay. So that's 2.84, 2.83. So the voltage drop is not the same across all LEDs. So across the red one it's about 1.8, and across this one it's about 1.9 or 2. What was it? 1.9. It was 2 point something. Short-term memory here. 2.8. Okay? So that's an interesting thing. But what happens if we put 2 in a row? You see some interesting things happen. I wanted to do this because it's kind of cool. I just pulled the... So we put 2 in series, so one after another. They're still in the circuit. They still turn on, but now they're pretty dark. And again, we'll turn this on. Everyone's going, why doesn't he untangle his wires? Good point. Nobody knows. And now it's 2.5 across that one. It's a bit strange. 2.4. What's across here? 0.2 volts. So are we running out of I think we're running out of battery power here. They're fading. Wait, are they fading in front of me? Okay, they are. Alright, so actually there's very little voltage going across here. Most of the voltage is being taken up by this. And so we can assume that they take at least 2.5 to actually turn on. And in fact, if we put in another one, so we've got 3 in series and 1 resistor, they don't even turn on at all. There's nothing there at all. But there is still a voltage drop across them, which is kind of interesting. So there is still 5. So now, if you look across the resistor, there's no voltage drop across the resistor because there's no actual current flowing. Well, there's like an incredibly tiny amount of current flowing through this. And that's because the forward voltage drop for each of these adds up in order to get them to actually conduct. So the total forward voltages for each of these add up to more than 5 volts, so no current's getting through because there's just too much blockage in the way. There is 5 volts registering though, but there's not getting any current through. And the interesting thing about this is if you actually measure each one with this particular multimeter, you can see that the voltage it says across here is 0.4. So each one is about 0.4, that one's 0.75. And this one's 0.74. Now, if you add all those things up, they don't come. It comes to less than 2, right? So it's 75 plus 75 plus 0.4 or something is about 2 volts. So that's kind of a strange thing. It's like, well, how did you get 2 volts by adding each of these up? Shouldn't they all add up to 5? Because across the whole thing, it's 5 volts. And I think that's just because looking at this from the point of view of here, this has a very high resistance. And this thing here, when you get to high resistances, it's not going to be able to measure things as well as when it has lower resistances. So it's kind of getting confused by, that's what I think is happening here. Because it's not just disappearing. It's not like there's no, in between the 2 wires is the extra 3 volts or something. This is actually working properly. It's just this thing is having problems because this will be like millions and millions of ohms, and the sort of resistance of these things is, so these have a high, because they're measuring voltage, they don't want to be part of the circuit, so they have a pretty high voltage, and that voltage might be like 5 million ohms. I don't know what it is, but it's a high voltage, I mean a high resistance, because it doesn't want to interfere with everything. We're going to go through this with parallel circuits. But when the thing it's measuring also has a very high resistance, then you'll get things mixed up because most of the current will start going through here and things like that. And so, because there will be an easier path to go through the multimeter than it will be to go through the LED, and so that will muck up all the results. So remember, when you're measuring things, you are actually affecting the circuit. So we'll go back quickly to here, and how much time we've got? We've got 12 minutes, so we're going okay. That was an interesting little side thing. And now we're just going to go back to what we've learnt. So that one, voltage divider. Okay, we'll go with that. But now we're going to look at this, and I've done actually the answers on here. So this is my thing. So here we have our little circuit. So we've got 5 volts at the top. So I've gone back to 5 volts from my thing, and not 6 volts. This is a resistor, and I'm going to draw it the square box style this time, and that's meant to be a question mark. And here's my LED, and it could be the red or the blue. So I measured it before, and I thought that the blue forward voltage was about 2.8, and the red voltage was about 1.9. I'm actually just going to ignore some of these numbers, but the big thing to take home is that they do have some rough forward voltage drop. And I mean, this will probably be slightly different between each LED that you get, even if they're the same color. And different brands and different batches of LEDs will probably have different ones too. I don't know. So the thing here, I've written down that the voltage across, the voltage across the LED. This is what this bit means. So this section here is 1.9 for red and 2.8 for blue, and so the remaining voltage, whatever the resistor is, given we have 5 volts, is going to be, for the red one, 5 volts minus 1.9, which is 3.1, and for the blue one, it's going to be 5 volts minus 2.8, which is 2.2. So this is the voltage that we can kind of roughly think will go across the resistor, whatever the actual value of the resistor is, because we can sort of pretend that the voltage drop is fixed across here. It's not, as we've seen, exactly fixed, because there is some internal, so there's some internal resistor in here as well, and that's still making some sort of voltage divider. So there is still some shifting of the voltages between these two things. But it doesn't matter too much when we're just doing this, because you're just approximating things. So to get back to the last bit, this is going to be a good timed one, I think. So going back to what we had before, V equals IR is our Ohm's law thing. That's how I always remember it. And then we go to here, and then we've got, so rearranging this algebraically, I can then say that I equals V over R. So if I put the R over there, so divide both sides by R, and then I get I equals V over R. So that's now how I will calculate. I've done this the wrong way around, haven't I? Oh, okay, it doesn't really matter. Maybe I should do one more sheet. Oh my goodness, then the wrong way around. We really want to work out what the resistance is given what we currently want. So I don't know why I did it this way, but we'll just do it this way. So let's just say we're going to stick in. So at the moment we've got a 330 ohm resistor in there. So what is the current going to be for 5 volts? Well, in the first case for the red one, I'm just pretending that there's 3 volts across the resistor for red. I've just rounded it up. So 3 over 330, the answer is, because it's 330 ohms, V over R, 3 volts over 330 ohms, we get 0.009 amps, and that's 9 milliamps. So that's a good value, because the thing we're aiming for here is we want the current that goes through the LED to be small enough that the LED won't get hurt. So if you don't have high enough resistance and you send too much through, the LED will let through a lot of current, right? But if it's too high, it will burn out, probably because you can kind of imagine there's that internal resistance, and if there's too much going through, it will heat up and break it or something like this. And in the case of the blue one, there's 2 volts going through the resistor because there's more voltage going across the LED. So you end up with less current. So with different LEDs, you're going to get different amounts of current. So in this case, we've got 6 milliamps going through there. So we've got 7 minutes, and what I should have done, so that's the important thing to get from this, is that as you change the resistor, it's going to change the current that's going through both items, so both things in the circuit, because they're in series. So the current, as I said before, has to be the same for both the resistor and the LED. So the current was the same across this bit here. So that's another sort of fundamental rule. Things don't bunch up. The current doesn't bunch up here, or it doesn't like space out in different ways. It goes through evenly and will remain the same. So what we really want to do though is a different equation. I'll bring my backing sheet because I'm going to try this felt tip pen. Does this even work? Unfortunately, this means I'm going to have to turn. I was trying to avoid. That's completely broken. I was trying to avoid doing things on the side. I've found that I've got another camera actually, and it's quite a funky little camera, and it has a little better rotating. I might turn this on. A better rotating screen, so I might actually switch these things around. I'm going to have a lot. I've already got 2 camera mounts. Maybe I should see how it goes. So the other thing, it doesn't got good a resolution though, but it's a nice camera. So anyway, back to this. We'll do V equals I over R. What we really want is we want the resistance. So in this case here, we're going to divide both sides by I, and that will get us, if we rearrange and quickly do these things, V equals over I. Alright, so we know the voltage across the resistor. So in the case of the red one, so I said, and given that we have 5 volts going across the whole thing, so if it's different, if there's 10 volts going across, then there'll be a lot more voltage going across the resistor, because the voltage going across the LED will stay pretty much the same. So you're going to need a different resistor. So the red voltage is the voltage across the red resistor is 3 volts. Alright, so the voltage across the red resistor is 3 volts. And so we know what that value is, and we know what the current is. Let's just say that our LED is best performing when you have 20 milliamps going through there. So 20 milliamps equals 0.02 amps. Alright, so you have to convert it around. So that's millionths of an amp, not millionth, thousandth of an amp. So 20 thousandths of an amp equals 0.02 full amps. And this thing requires that you kind of match up the units. So if you're talking about volts, you have to be talking about amps. And if you're talking about ohms, so if they were all millivolts, milliohms, and milliamps, then you can do the whole thing together. But if they're different, it mix it up. So in this case here, we now have the resistance we require for the red one is going to be 3 divided by 0.02, which I feel bad doing this on a calculator because I should do it algebra by writing it out as things. But let's do this. So 3 divided by 0.02 equals 150. So the answer is 150 ohms. So I think we're running a bit low on time. If we wanted, with 5 volts going across here, and we were using a red LED, and we wanted the best possible light, so the optimal current is 20 milliamps, then the resistance we would need would be 150 ohms. And of course, if we did this with the blue one, right, well in this case the voltage across the resistor is actually less because there's more voltage going across the blue LED. So we do the same thing, and let's just pretend that 20 milliamps is also the target current we want for this. So now we've got 2 divided by that, which is going to give you a nicer number. It's going to be 100 ohms. But let's just put it through the calculator. And so in the case equals 100 ohms. So in the case of the blue LED with 5 volts, I would actually be better off with a 100 ohm because that will give me the same current going through as with 150 ohms in a red LED. But well, which is the current that we want for the maximal brightness. So it differs depending on it. So if you want to be exact, you need to know what the forward voltage drop is across your LED, and how much is going to be left therefore over the resistor. So I hope that kind of helps things understand. And one more little bit. So obviously, if I had 10 volts going across the whole thing, so it's 10 volts from across the resistor and the LED, and we were doing our blue thing, so we just pretend that the blue requires 3 volts. It has a forward voltage drop of 3 volts. Then we're going to get, in this case here, so the resistance, and we'll put 10 for 10 volts of the B, is going to be 10 minus 3 over 0.02, which is going to be 7 divided by 0.02, which equals 350. So we almost got it out of time, but 350 ohms. So the only point with this is if there's higher voltage going across here, then you're going to need a larger resistor in order to keep the current down. And there's one last thing that if we had a bit more time we could talk about, but we're going to talk about it later on, which is about power dissipation. So if the voltage is mostly, in this case with 10 volts going across the resistor, well the resistor has to do something with that, and what it's basically doing is it's generating heat. So you can't feel the heat because it's too tiny amount of power there. But as you get higher voltages going through there, then you're going to get more heat generated. And this is the reason why this is like a big resistor, is because it can handle more power going through it. So we're going to talk about power going over things later on, but you won't have to worry about that for now. But that's just one interesting thing for later to talk about. But I hope that kind of makes you helps you understand what the resistors are and all that kind of stuff. And according to my thing, we've got 20 something seconds left. And I didn't get to show you my cool little car. So I'm working on another project, and this is my little car that I made. And I'm actually kind of proud of it. I don't really do woodworking, so hopefully this is going to do something cool the next thing. But anyway, like, share and subscribe, and I'll see you later.